Hello everyone. This video covers section 5.6 in the book. So this is section 5.6, which is called multi-step methods. Up to now, all the methods that we have discussed, including Euler, Runge-Kutta methods, Taylor of order n, and so forth, are called one-step methods. So far this is what we've done. And the reason why they are called one-step methods is because the difference equations usually looks like this. Wi plus 1 is equals to Wi plus h for some function phi of t iwi, where I is equals to 0 all the way to n minus 1. And you notice here, the I plus 1 depends only on the previous value. So that's why they're called one step. And all the methods that we've done so far are one step because they all depend just on the previous value, and the function here depends only on the pretty much the previous value. So the main idea in this section is that we're gonna use not just the previous one, but all the previous values. So therefore, for example, if you wanted to find W3, then it will use not only W2 plus W1 and W0 in the calculation. I mean, it is obvious that this one uses this and this uses this, but in the multi-step methods, this uses all the previous information, just like this one use all of this and so forth. So here is the official definition. An m-step multi-step method for solving the same initial value problem that we've been solving all along is the following. So notice that Wi plus 1 depends on Wi, I minus 1, and so forth. So up to m steps. And then the function phi also depends on the previous values up to, but including the value itself that you're trying to compute. And here I goes from n minus 1 all the way to n minus 1. The value for a0, a1 all the way to an minus 1 these are constants. Okay, these are constants, and so are v0, v1 all the way to vm. Notice how usually the values for am minus 1, an minus 2 in the previous methods we did, since we only have one of them, the value is usually 1. And on the method we're going to do right now is also, this is usually 1, but these are just constants in either case. And now, instead of also just having one condition or one starting point, you can have 2, 3, 4, all the way to n minus 1, depending on how many steps you want to use. Again, this part pretty much is this for the equivalent of one step, and this is equals to this if it was only one step. If Bm, which is this value right here, is equals to 0, so if Bn is equals to 0, then this method, the methods right here, the multi-step methods, are called explicit. And explicit means the wi plus 1 is only in one side of the equation. Okay. Which pretty much all the methods we done so far were explicit. Because notice here you have wi plus 1 here and also wi plus 1. So if this is equal to 0, this is gone. So therefore wi plus 1 will depend only on the previous values. Just like it was the case for Euler, Runge-Kutta, and so forth. Now, if the value for Bn is not equal to 0, then the method is called implicit. And now implicit means that wi plus 1 is in both sides of the equation. Okay. And therefore, you will have to solve for wi if you want to apply the method. Now, to solve for wi plus 1 is not always possible, and this could be a big problem. Now we'll see at the end of the video there is a way to get around it, but if you have an implicit method, that means you have wi on the left side and wi on the right side, and then you will have to combine the two and solve, which is not always the case. For example, let's say that you have y equals to e to the y. This is the most famous example. It is impossible to solve for y in here. So therefore, if you end up with something like this, you won't be able to apply this method. And again, there is a way to get around it, but you technically cannot solve this in an explicit form. Therefore, for the rest of the video or the rest of the section, we're going to look to only two kinds of methods, either explicit or implicit. Implicit is also called a closed method, and explicit is usually called open. Now, if the methods are open or explicit, we're going to call it the Adams-Bashfort technique. And it could be second order, third order, fourth order, just like the Taylor methods. So here I'm just going to give you an example of how a fourth order method looks, and then in the next page or next pages we'll see how we can get these formulas, or where did these formulas came from. Again, Adams-Bashfort is going to be pretty much always explicit, which means that on the right side you don't have any wi plus 1. This one is of order 4. Notice how you need to have 4, technically you can call it initial conditions, which this will pose a problem, because usually when a problem is given like on this form, you technically only have this condition right here. So therefore, to generate these remaining values, you usually use Runge-Kutta method to produce these values. And once you produce these values, then you can apply this method. For example, if you remember the equation we've been solving all along, y prime is equals to y minus t squared plus 1. T is between 0 and 2, and y0 is equals to 0.5. You remember from we use the Runge-Kutta method to solve this equation. And if we use the values from the Runge-Kutta of order 4, where h was equals to 2.2, from there W1 was equals to 0.8292933, W2 was equals to 1.2140. I mean, you have these values from before, so you can check. We have a table with these values. W3 was 1.648920. Remember that this was y of 0.2, this was y of 0.4, and y of 0.6. Therefore, if we want to use now this method to approximate, let's say, y of point A, which is approximately equal to W4, therefore this should be equal to W3 plus 0.2 over 24, that will be 55, f of 0.6, and then W3 minus 59, f of 0.4, W2 plus 37, f of 0.2, W1, and then finally 9, f of 0, W0. Once you plug in all the values, simplify, this is around 2.127 2A92, which actually this is not as good for this particular example, as the result obtained using Runge-Kutta of order 4. So pretty much this method is not superior to the Runge-Kutta, but you'll see in a little bit how you can modify it to make it a little better than Runge-Kutta method. Now the Adams-Moulton technique of order 4, which again you will see soon that there's nothing special about order 4. It could be order 2, order 3, and so forth. This is an example of a implicit or close technique. Okay. Again, the main feature of implicit means that you have wi plus 1 in both sides. So therefore, before you can apply the technique, you have to simplify and combine these two into one, and then from there you will get a new method. And again, it's not always possible to do that. Now here in our case, this is actually possible, because here WTI plus 1 plus WI plus 1 is technically just WI plus 1 minus TI plus 1 square plus 1. So here you multiply by h over 24, and you have WI plus 1 equals to WI, and then this keeps going. You can actually combine this with this. So in this case, it will be possible, and you can apply this method too, just like the one we did before in the previous example, or right here. Now, the next obvious question is, well, how do we get these equations, or where do these equations come from? And by these equations, I mean the Adams-Bashfort and the Adams-Moulton methods. Now, there is more than one way to derive this, and in the homework question, they ask you an alternative way. Remember that Taylor series is always a good choice. But here, the way the equations are derived is going to be based on the Newton and backward difference formula. And we talk about this in detail, I believe it was in section 3.3. So you may want to check that section before you continue with this. Remember that we are actually trying to solve this problem. Remember, y prime equals to f of ty, where remember that y is a function that depends on t, so this is very, very important. Now, if you integrate both sides, okay, notice that the integral of y prime dt, well, technically is just is y, because the derivative cancels the integral, and this goes from ti to ti plus 1. Well, this should be obvious, but just to make sure you get this is equals to y of ti plus 1 minus y of ti. And that's how we got this part. Okay. Now here we have a problem, because we know this is equals to this, but we cannot integrate this unless you have the solution to yt. So this part requires to know yt in order to integrate. But if we already knew what yt was, there will be no need to do any of this stuff, because then you already know the answer. So instead, what we're going to do is we're going to replace pt by interpolating polynomial. And we did a lot of that before in chapter 3, so that's why I say the basis is going to be the Newton backward difference formula. So we're going to replace this by a polynomial. Also, we made the assumption that yt is around wi, and we have used this assumption many times before. Now, the reason why at the moment the backward difference is very appropriate, or the most appropriate, is this, because remember, if you're trying to find, let's say, w4, that one is going to need that, w3, w2, w1, w0, so you're going backwards in time. So therefore, to derive the Adams-Bashfort, remember that these are the explicit method, or the explicit m-step technique. We're going to need the backwards difference polynomial, or the backward difference polynomial, which we're going to call a pn minus 1 of t. So this is going to be the backward difference polynomial, which requires the following information: ti, f of ti, y of ti, and then ti minus 1, f of ti minus 1. So you can see that this is pretty much going backwards, and so forth, until you go to the last step, which in this case it will be the m step. This will be f of ti plus 1 minus m, and then y of ti plus 1 minus m. Therefore, using this information, you can write f of t, y of t as pn minus 1. So this will be the interpolating polynomial of degree n minus 1. So this is a interpolating polynomial of degree n minus 1 plus the error term, which will be the n derivative evaluated at Cauchy y of Cauchy over n factorial will be t minus ti minus 1 all the way to ti plus 1 minus m. Now, if you integrate now both sides, so where pt is replaced by all of this, or f of ty is replaced by all of this, then you will end up with the following equation. And I don't expect you to get this or to memorize the steps, but it's not a bad idea to look to the derivation of this. This is very similar to what we did in section 3.3. So once you simplify everything, this equation, this one, I'm gonna give you all of this, where this part is the error term. There is a typo right here, so this should be ti, so this part should be y of ti, and so is this one, and so is this one. All right, also remember from chapter 3, nabla, that was the name of the symbol of f of ti, y of ti, by definition means y of ti minus f of ti minus 1, then y of ti minus 1. Okay, so this equals to this, and then you have nabla square of f is the same thing as nabla of f. One more thing here, Cauchy is between ti plus 1 minus m and ti. So this goes with this. Now, the last part here is when you want to find the error, you usually have to evaluate this part, which is not hard to evaluate this, but it can be pretty annoying to evaluate this integral. So therefore, there is a table that you can just use to figure out what those values are. For example, if the value for k is equals to 3, this part that is highlighted is equals just to 3 over 8. You can expand the whole thing yourself and see for yourself, but you can just use this table to make your life easier when you need to compute these values. All right, so let's see how we use the previous formula to derive any of the Adams-Bashfort techniques. Okay, so remember the formula was this, y of ti plus 1 is approximately equals to y of ti plus h. Then this is f of ti, y of ti plus 1/2 nabla of f of ti, y of ti. Then 5/12 nabla square f of ti, y of ti. And this technically keeps going, but here we want to derive the 3-step. So that means that m is equals to 3. So we don't have to go any further than this. And then we need a separate formula for the error. Okay, recall the nabla of f of ti, y of ti, by definition is equals to f of ti, y of ti minus f of ti minus 1, y of ti minus 1. So this part is equals to this. All right, so then nabla square of f of t y ti should be the same thing as nabla of f, which will be nabla of f of ti y of ti minus f of ti minus 1, y of ti minus 1. So you can break this into two pieces, and then you just apply the formula to each of them separately. So again, the algebra to this is actually not that messy, so it's actually pretty easy to do. Just be careful with the indices. So this first part, again, it will be f of ti y of ti minus f of ti minus 1, y of ti minus 1. And the second part is going to be f of ti minus 1. This will be y of ti minus 1 minus f of ti minus 2, y of ti minus 2. So you simplify this will give you f of ti y of ti minus, you can combine this will be 2 f of ti minus 1, y of ti minus 1. And then finally this will be plus f of ti minus 2, y of ti minus 2. Therefore, this part is going to be equals to all of this. Now, if we plug in this part into here and this into here, we will get the following. The y of ti plus 1 is equals to y of ti plus h. This will be f of ti y of ti plus 1/2 of f of ti y of ti minus f of ti minus 1. And then plus 5/12 times f of ti y of ti minus 2 f of ti minus 1 minus 1. Then finally the I minus 2. Okay. Then once you simplify everything, the algebra is very, very easy from here. Because for example, you want to simplify this part, you have this, this, and this. So technically, you want to add 1 plus 1/2 plus 5/12. Well, clearly this is 23/12. So this is pretty easy to check. Therefore, you will end up with the following: y of ti plus 1 equals to y of ti plus h over 12. And it's going to be 23, which is this 23 we got. F of ti, y of ti minus 16, f of ti minus 1, y of ti minus 1, plus phi f of ti minus 2, y of ti minus 2. Therefore, the three-order Adams-Bashfort method, Bashfort method of order 3. Order 3 is going to be the following. You need W0, W1, and W2 to start the problem. Then the difference formula is going to be Wi plus 1 equals to Wi plus h over 12. This will be 23 f of ti Wi. So this is the one you're going to use to compute the values. Wi minus 1. And then finally plus phi f of ti minus 2 and Wi minus 2. As you can see, it wasn't that hard to get to this formula. You can do the same thing for if m is 2, if m is 4, m is 5, and so forth, using this exact same formula. You just have to be careful how far along you have to go in here. But you can do this formula easily to get any of these formulas with m equals to 2, 3, 4, 5, and so forth. As I mentioned before, you can also get these formulas actually using Taylor series, also using the Taylor method of order n, and also using Lagrange polynomials. So there is more than one way to get to this, but probably this is the easiest way because you already have a formula. All you have to do is manipulate this to get the order that you want. Let's now take a look at the local truncation error. Remember that tau I plus 1 stands for the local truncation error. Also remember on the pass, and on the pass it means the last few sections, ti plus 1 of h was equals to y of ti plus 1 minus y of ti divided by h minus some phi function that depend only on ti and y of ti. So this is what we have before. But now phi of ti and y of ti depends on previous values. So for the Adams-Bashfort method that we just derived, okay, for order 3, the error, you look at the formula, the error for this method was h to the 4, the third derivative evaluated as on mu I y of mu I, and this is negative 1 to the third times the integral from 0 to 1 or minus s choose 3 ds. Remember that I give you a table in the previous page where you can evaluate this, and from the table this was equals to h to the 4, the third derivative evaluated at mu I times this was 3/8. So when you use the table, all of this is equals to this. You can also integrate the whole thing if you wanted to convince yourselves, but you can just use the table and it will tell you this is just equals to this part. Remember that y prime was equals to f of t y of t. So this implies that y to the 4 derivative is the same thing as the third derivative of f. So using that, we can rewrite this as h to the 4 or 3h to the 4 over a, the fourth derivative of y evaluated at mu I, where mu I is between ti minus 2 and ti plus 1. Therefore, for this particular method, t of I plus 1 of h, which by definition is y of ti plus 1 minus y of ti divided by h, and if you divide the whole thing by h, notice how this h disappears. So then you'll end up with 1 over 12, this will be 23 f of ti y of ti. So it's pretty much the same thing you have before, except the h is not there. Okay. Plus 5 f of ti minus 2 y of ti minus 2. Okay. Which by definition then this will be 1 over h times the error we found, which is this one. So this will be times 3h to the 4 over a, the third derivative, which we already simplified this to be y, the fourth derivative of y. So then this will be the fourth derivative of y evaluated at mu I. So therefore this should equals to 3h over 8 times the 4 derivative evaluated at mu I, again where mu I is between ti minus 2 and ti plus 1. So again, just to recap, you can see that to derive the method like this is not that tricky. You just have to follow this formula and be careful of how far you have to go. The same thing for the error, and then for the truncation error. So this is probably the most important part of this section, had to come up with these formulas and the truncation errors. In the next page, we see many of these methods, so it just has the solution, and one of the main things you need to know is how to derive all of those methods, which is exactly what we did in this page. Here we have 2 examples of explicit methods and 2 examples of implicit methods. The first one is the explicit, and this is a 2-step, and here is the difference equations. You should try to get this by yourself. This is actually pretty pretty easy because it's 2 steps. We did a 3-step already. You can also do the same thing for the 4th step and the 5th step. And these are the truncation errors. This is the one we just got right now. And you should be able to get this. Something like this is a very good question to do on the next test, either this or to get the 4th step or even the 3rd step. So to be able to get these formulas and the truncation error is therefore something that most likely will be in the exams for sure. Now, it is interesting to compare the truncation error of the 2 kinds of methods between the implicit and the explicit. For example, let's look to the 3-step, this one, and this one. So this is the truncation error. This one is the truncation error. So you can see how in general the truncation error for the implicit is smaller. So therefore the implicit methods tend to be more stable or more accurate, which means that they have a smaller round of error for the most part. But like I say before, you usually for implicit methods, it requires that you solve for wi plus 1 explicitly, which may not be possible all the time. However, there is a way to combine implicit and explicit methods at the same time to go around the issue of not being able to solve for wi plus 1 by itself. I already give you an example of when that's not possible. Another example will be this. You have y equals to ln y. It's impossible to solve for y because if you do this, you end up with e to the y equals to y, and again you won't be able to solve for y by itself. But if you combine the explicit with the implicit methods, you can get around this, and that's what we'll do in the last page. The last thing we'll be talking about is called predictor-corrector methods. So like the name implies, we're gonna use one method to predict a specific value, and then you're gonna use a second method to fix or correct the answer. The predictor is gonna be the explicit method that we talk about, and the corrector is gonna be the implicit method. Okay. This is the Adams-Bashfort 4-step explicit method, and this one is the Adams-Moulton, also 4-step implicit method. So by using this predictor-corrector technique, you don't actually have to solve for wi plus 1 as before. So if you want to use an implicit method by itself, remember you have wi plus 1 on the left side, and then you also have wi plus 1 on the right side, and you had to algebraically solve for wi plus 1, which I already mentioned a couple times, it may not be the case. So by doing this predictor-corrector technique, you don't have to worry about doing this anymore. So the idea is very, very simple. So you're gonna use first an explicit method, and let's say for the purpose of the example we're gonna do, we're gonna use the 4-step Adams-Bashfort for the explicit and the Moulton for the implicit. Now remember that only this part is given, so you need to find this. So you need to use a different method from the past. Usually the best is to use the rank kata or order 4 to approximate W1, W2, and W3. Once you do that, we're going to find W4, and it's the same technique for W5, W6, W7, and so forth. Depends how far you want to go. So the reason why I call this W4P instead of just P, the P stands for the predictor, but this is nothing more than W4, and also to distinguish between this W4 and this W4. So you compute this value, which should be straightforward. There is nothing that can go wrong in here. You can compute this, and this easily once you have gotten the values from the rank-kata method. Once you have done that, notice that how we also have W3 equals to W3. So then to use now the corrector, so this will be the corrector, then you already have this value, this one, and this one. So instead of using W4 in here, we're going to use the predicted value. So whatever is the answer to this is going to go in here. And then this will give you the new W4, which should be a corrector of a improvement of the previous W4. And then you're just repeating the same method for W5. So after this, you will get W5P. From there, you get W5. And then you will get W6P. Will give you W6, and so forth. Remember, I mentioned this at the beginning of the video. By itself, the rank-kata method is actually better than the Adams-Bashfort or the Adams-Moulton by itself. But by doing this predictor-corrector technique, it actually outperforms the rank-kata method. For example, let's use the same example that we have been using all along. Remember, y prime is equals to y minus t squared plus 1. T is between 0 and 2. And the initial condition was equals to 0.5. So we apply the method the way I say before. You need to compute these values first using the rank-kata method of another technique. Then find W4P, which is the predictor. You plug it into the implicit method to get the corrector. And then once you do that, so now you will have W0, W1, W2, W3, W4, and then from here, the next step is to get W5P first, then you find W6 and so forth. So you do that, you get the following table. So this table shows the results of the combination of the predictor and then corrector method. And this one is the rank-kata of order 4, which was the best that we had before. Okay, so you can see that especially in the last part, this one is more accurate than the rank-kata. Not much accurate, but it's more accurate, as you can see from here. This is 1013, this is 1089, this is 799, this is 906. So therefore this does make a difference if you follow this predictor-corrector technique. And that's it for this one.